In the last class, we discussed about sand replacement method, determination of in situ density of the soil, and in situ density of the soil can be determined by two methods. One is a core cutter method and second one is a sand replacement method. I discussed core cutter method in detail and sand replacement method we will discuss when you come in offline. Right? Now we will go ahead. The next topic is here, that is a sieve analysis. The sieve analysis means what? Sieve analysis means we are understanding the particle size distribution in the soil. See, this is a soil and here various diameter particles are there. Some are very small, some are very small, and some are very big. Like that, this entire soil mass is constituted with many different diameter of the particles. Okay. I cannot take one out and what is the diameter. I cannot take like one and each and everything like that. Therefore, what I do, I will use a sieve. Sieve means it's like a cylindrical structure like this, and it will be having some opening space here. If I put a soil here and shake it in a horizontal direction and in a vertical direction, then the soil will come down, and these soil particles diameter will be lesser than the size of the sieve. Correct? The particle size which are coming down are lesser than the size of the sieve. Like that, I will do some sieve analysis by considering set of sieves. I will consider set of sieves, and by doing this I will come to know what particles, what percentage of such different particles, what percentage of 4.75 are there, what percentage of 2.36 mm are there. Like that, each and every particles I will get it, and I will draw some graph and all, so that I will understand the particle size distribution in the soil. This I will explain when you come offline. Okay, here it is written. See, it is difficult to understand through online, so when you come to offline classes, I will explain this one. Therefore, we will keep this concept pending. You just understand that sieve analysis is the test to understand particle size distribution in the soil. Next heading is hydrometer method. Hydrometer method. See here, particles which are greater than 75 micron. 75 micron means very small size. Do you know khadi? Khadi shirts will be there. Khadi shirts approximately the space between the two threads in the khadi, or otherwise the opening in the khadi shirts, will be approximately near to 75 micron. From this you can understand that what is the you can visualize what is the size of 75 micron. If the soil is passing through 75 micron sieve and the passed soil passing through 75 micron size sieve, that soil particle size distribution is very difficult. You cannot understand what percentage of 75 micron soil is there, what percent of 60 micron soil is there, what percent of 50 micron soil is there, 25 micron soil is there, 2 micron soil is there, 0.1 micron soil is there. See, these microns getting the particle size distribution and percentage of these particles is very difficult through sieve analysis. Therefore, we have invented one method that is called as hydrometer method. This method also I will explain you when you come offline. It is very difficult to explain through online this hydrometer method. Okay, now still if it continues, if this lockdown continues further, then I will make an arrangement. I will go to the lab, I will conduct the experiment, I will perform it. But still we have a opportunity to learn this hydrometer method offline. Therefore, I will not cover in this one. We'll go to the next concept. Consistency limits of or ATTER limits. Now, this we can study in online, because only theory we need to understand this, what is consistency limits and what is ATTER limits. This I will not call you for offline, I will explain in the online only. Okay, now look at here. Okay, we'll understand very clearly. See, this is the soil. I will put a little amount of water, very little amount of water. when I put a little amount of water, now initially without water, soil behaves like a dry. Soil is a dry and behaves like a powder. Correct? Powder. Soil is behaving like a powder. When I put a little amount of water and mix it thoroughly, then I can have a small lumps. But these lumps are collapsible. If I put a small load, then it will collapse. If I put a little small load, then it will collapse. You know? Like that, it will be a lump. It will become a somewhat wet soil, but with a small lumps. And lumps are quickly collapsible. If I put a more amount of water, then this soil becomes somewhat like a paste. Somewhat like a paste. Okay, paste means what? This can be very hard paste, or it can be a smooth paste. It can be a smooth paste. Right? Hard paste means you can mold into any shape. You do Ganapati, right? You take a soil and you put a some amount of water. You take a clay and you put a water and you will make one mold. And after that, you will take a small part of that and you will prepare head. And a small part again from here you will take and you will make that what a hand. You know, see. And you will take a small part and you will make a this one. Small part and then you will make a this one. Then this become a Ganapati. See means the amount of water you added to the soil and this soil paste, you can give any shape to that one. It is not crumbling, it is not collapsing, it is not making a cracks. If it is a dry, then you will observe many cracks in the Ganapati. Therefore, what you do? You add a little amount of water. When you add more amount of water, Ganapati will collapse it will flow like a liquid. Therefore, you will add that much of water. By adding that, it should behave like a plastic material. It will behave like a plastic material. Means you can make into any shape. It will not crumble. Then again, if you add a more amount of water, it becomes slurry. It become a mud. Then mud, if you put on the ground, it will flow like a fluid. It will flow like a liquid. Understood? Means only one type of soil only I have. This is behaving like a dry soil. That if I add some amount of water, then it is behaving like a semi-solid. That is again behaving like a plastic material. Then again by adding some amount of soil, it is behaving like a liquid material. The same soil, see the behavior is different. Behavior is different with respect to what? With respect to addition of water. This change in the study of change in the behavior of soil when water is added is called as consistency of the soil. That is called as consistency of the soil. Then understanding at what point it is behaving like dry, at what point it is behaving like a semi-liquid, at what point it is behaving like a plastic, at what point it is behaving like a liquid, that those limits are called as consistency limits. This entire experiment is first studied by ATTER, scientist name. Therefore, that is called as ATTER limits. Very nice now. That is there. Then Atterberg says that what Atterberg studied here is Atterberg considers volume in x-axis, water content in the x-axis, volume of the soil in the y-axis. He says that when zero water is there, then soil will have its own volume. See, this is a three-phase diagram. Water is not there, means 0% water content. Water content is 0%, but still it has a volume. See, this is a volume, means it has a volume. This much of volume is there. Then I added a little amount of water to this one. The volume not changed, constant. Again I added a water. Then volume not changed. Again I added a water. Volume again constant. Then onwards, if I add a water, volume change. Volume is increasing. Therefore, I will get volume is increasing. That you can see here. This is a water content in x-axis and volume of soils in a y-axis. Then at water content 0, soil is in a dry condition, therefore dry volume Vd, and this is a graph. This is a graph, and from here it is going like this. This is the graph. Okay, don't worry about this angle. Okay, and these are the things. Just you think that this is a old graph, and here at a particular point, this point, what you can call, this point you can call as, this point has a some water content, from which if you increase more water than this, then its volume is changing. If you decrease the volume water than this, then volume is constant. Means from this point the swelling starts, or otherwise up to this point you can observe shrinkage. Before this one, shrinkage will not happen, volume reduction in the volume will not happen, therefore we will call this point as shrinkage limit. This is shrinkage limit. Then again, if I add a water to this one, then this one initially it is in a solid state, and again if I add a water to that, it behaves like a semi-solid, collapsible lumps, semi-solid, it is behaving like a semi-solid. Then it will behave like a semi-solid, and after a particular water content it starts behaving like plastic material. Then when it starts behaving like plastic material, that starting point is called as plastic limit. That is called as plastic limit. Then it is behaving like a plastic. Then after that, if you add a little amount of water more than this, then it behaves like a liquid. Then at that particular point of water content is called as liquid limit. Liquid limit. See the meaning of shrinkage limit, the meaning of plastic limit, the meaning of liquid limit. See the video, go back and pause it, understand, and again see it. Okay, by doing that you can draw the definition for shrinkage limit, plastic limit, and liquid limit. Just I will go on telling the definition, you pause the videos and write it down. Shrinkage limit is defined as, it is the maximum water content up to which there won't be any increase in the volume observed. One definition. Shrinkage limit is defined as the minimum water content above which the increase in the water content causes increase in the volume. Two definition for shrinkage limit. Third definition for shrinkage limit. Shrinkage limit is the minimum water content up to which no change in the volume observed. For shrinkage limit, fourth definition. Shrinkage limit is the minimum water content to make soil saturated. Fourth definition. All meanings are same. Just you think which is good and which is bad. Next, plastic limit. Plastic limit is defined as a water content above which soil behaves like a plastic material. Plastic material. Understood? R, one definition. Second definition. Plastic limit is the arbitrary limit between semi-solid and plastic state. Semi-solid state and plastic state. Right? Next, liquid limit. Liquid limit is the water content at which the soil starts behaving like liquid state, liquid material. For this plastic limit you can add another. Plastic limit is the water content from which soil start behaving like a plastic. Okay. Next, liquid limit. Liquid limit is the maximum water content at which soil loses plasticity. Liquid limit is the water content from which soil loses shear strength. Shear strength. These are definitions for consistency limits. Okay, now in the next video we will see and one more thing, determination of liquid limit, plastic limit and shrinkage limit. How we are going to determine these in laboratory? For that we have an experiment. The first one is the Casagrande experiment. Casagrande experiment for liquid limit determination. Second one is plastic limit test. Plastic limit test. And the third one is the shrinkage limit test. These three experiments I will explain in offline. Okay, I will take that instruments and I will bring it to the class and I will explain that. If this corona continues, then I will go to the lab, I will do the experiment and I will upload it. Okay, I will share entire knowledge of geotechnical thing, engineering. I will not skip anything. Okay, no? Therefore, nothing to worry. But still, we have an opportunity to utilize the offline also. Therefore, I am skipping the very hardest topics and I am explaining in online smooth topics. Understood? Then relative density. Relative density is a index property for sand. It is an index property for sand material. Means we are comparing the density of the sand with its own loose density and with its own dense sand density. Dense density means our soil is here. This is a soil, sand. Whether this sand is, how much it is? If it is a sand density is 1.5 gram per cc. Think like this. Then when I put this sand very loose state, what might be its density? It might be 1.2 because it is very loose. When I make it very tight, that I compact it very hard, I will put a lot of load, I will vibrate it, I will make it each and everything compaction, a possible compaction. Then I will increase its density. How much I can increase? I may increase at 1.8 density. See, the maximum possible density of the sand is 1.8, for example, and minimum possible density of the sand might be 1.2. Then in my field I have a 1.5 field density. Then I will come to know that my sand is good or bad. This is somewhat in between. If I have a field density 1.7, my sand is good. If I have a field density 1.3, my sand is bad. This idea I will get it from relative density. Therefore, this also I will explain in the offline mode. What is relative density when it is asked, then you just remember this concept that we are comparing field density of the sand with the loosest state to the densest state. That is expressed as E max minus E divided by E max minus E minimum, expressed in percentage. Okay, now next comes classification of soil. From the next class onwards, I will explain this classification of soil in detail in online only. We will not wait for offline for this classification of soil. Thank you very much.